myself Daniel Patil, roll number 6. In this video I am going to discuss about the property of a Laplace transform, which is the first property, linearity property. It can be defined as the a into f of t plus b into g of t plus c into h of t, where a, b, c are the constant and f of t, g of t, h of t are the functions. So by using the Laplace we can find Laplace of a into Laplace of f of t plus b into Laplace of g of t plus c into Laplace of h of t. So this formula is given by the linearity property. So we can find the proof of linearity property such as, so by using the Laplace of this function, Laplace of a into f of t plus b into g of t plus c into h of t. So by using this is equal to the taking the definition of Laplace transform, which is integration 0 to infinity e raised to minus st into f of t. So integration 0 to infinity e raised to minus st into our f of t is the a into f of t plus b into g of t plus c into h of t. So we can find the integration back separately, such as integration 0 to infinity taking constant as a common a into f of t plus integration 0 to infinity b into f of t b into g of t plus c integration 0 to infinity e raised to minus st. By using the definition of Laplace transform, we can find the integration 0 to infinity e raised to minus st into a into f of t plus b into g of t plus c into h of t. So taking integration separately to the function, take a as a common, integration 0 to infinity e raised to minus st into f of t plus integration 0 to infinity taking b as a common, e raised to minus st into g of t plus taking c as a constant, 0 to infinity e raised to minus st into h of t. So as we know, this is the formula, this is the definition of a Laplace transform, which is equal to the a into Laplace of f of t plus b into Laplace of g of t plus c into Laplace of h of t. So which is equal to the RHS. So I can give one example of linearity property, then you will easily understand. The example is cos sin 2t into cos 3t. So we cannot find this simply Laplace of this function. So by using the sin a into cos b formula, which is nothing but the sin a into cos b is equal to the 1/2 sin a plus b plus sin a minus b. So putting this value in this formula, 1/2 sin a plus b is nothing but the 2t plus 3t, 2t plus 3t plus sin 2t minus 3t. So solve it as 1/2 sin 2t plus 3t is nothing but the 5t plus sin 2t minus 3t is the minus t. So as we know, the sign of minus theta is nothing but the minus sin theta. So we can use this 1/2 sin 5t minus sin t. So taking a Laplace of this function, taking Laplace of this, taking Laplace transform, can find it by using which is equals to f of t, Laplace of f of t, which is equal to the Laplace of 1/2 sin phi t plus sin phi t minus t. Sin phi t minus t. So taking a Laplace transform, but we cannot find the Laplace of this. So by using the linearity property, which is equal to the 1/2 take common Laplace of sin phi t minus Laplace of sin t. So as we know, the Laplace of sin at is nothing but the a square a upon a square plus a square. So we can write this as Laplace of sin phi t is nothing but the 5 upon s square plus 5 square is 25 minus sin t formula is the 1 upon s square plus 1. So which is our required solution. Thank you. So I can take you one example of linearity property, which is a hyperbolic function. So let's find the Laplace of the sin hyperbolic at. So your f of t is sin hyperbolic at. So taking the Laplace of this, but we cannot find the hyperbolic function Laplace, but we know that the sin hyperbolic at is nothing but the e raised to at minus e raised to minus at divided by 2. So let's take the Laplace transform. So by using the Laplace transform, Laplace of f of t, by using also the linearity property, Laplace of e raised to at minus Laplace of e raised to minus at, which will be given in the as we know the Laplace of the e raised to formula, which is nothing but the take 1/2 as a common. E raised to at is the 1 upon s minus a minus 1 upon e raised to minus at is the s plus a. So by solving this, we can find the 1 upon s square minus a square. Sorry, 1 upon s square minus a. So we hyperbolic.
Friends, my roll number is 7 and today I am going to discussing about the examples of Laplace transform of elementary function. So first of all, before starting the example, we see the definition of Laplace function. First of all, Laplace function says that Laplace of any function is equal to the integration from 0 to infinity e raised to minus st into that given function whose integration with respect to t. So first of all, the first function is f of t is equal to 1. According to the Laplace definition, Laplace says that Laplace of any function is equal to Laplace of any function is equal to the integration from 0 to infinity e raised to minus st into f of t dot dt. So here from 0 to infinity e raised to minus st into 1 into dt. So the integration of e raised to minus st is given as e raised to minus st upon the derivative of minus st with respect to t is minus s and limits from 0 to infinity. So e raised to minus infinity upon minus s minus e raised to 0 upon minus s. So we know that e raised to minus infinity is 0 and 0 upon anything is 0. So and e raised to 0 is 1 and minus s is plus, so 1 upon s. This is the Laplace transform of the 1. And another example, here a function is given as e raised to minus 80. After this, we know the rule of indices. According to rule of indices, 1 upon minus of s minus a. Putting the limits of the function limits in the given function, and it comes as, we know that the e raised to minus infinity is 0 and e raised to 0 is 1. So it is 1 upon s minus a into minus 1. Laplace transform of the function e raised to at is written as 1 upon s minus a. Then the another example and it is f of e raised to minus at. Laplace transform of function minus at is equal to integration from 0 to infinity e raised to minus st into e raised to minus at dot dt. According to rule of indices, it is written as e taking the above function and it is written as e raised to minus t into s plus a upon s plus a. Here the negative sign is attached to the term s plus a and limits from 0 to infinity. Putting the limits in the given function, and we know that the e raised to minus infinity is 0 and e raised to 0 is 1. So it is written as e raised to. The Laplace transform of the function e raised to minus at is given as 1 upon s plus a.
Hello friends, myself Aditya Paul. Today's we take one example of a Laplace transform. So first we have apply the linear property of linear e raised to minus x into f of x dx. So here is 0 to infinity e raised to minus x into f of x is sin at into dx. So e raised to minus 80 upon s plus a in 0 to infinity e raised to minus s of t into sin 80 into dx. So here apply the Laplace transform and give the e raised to minus 80 s plus a into 0 to infinity minus s into sin 80 plus minus s into cos 80 dx. So e raised to minus st upon s plus a in bracket minus s into s sin 80 plus minus sin cos 80 dx. We have put the limits in it. So e raised to minus t upon s plus a upon minus s into s a upon infinity plus minus s into cos infinity dx minus never sin 0 becomes 0, so minus a upon s square plus a sin 80 is equal to a upon a square plus a square. Property as applied to 0 to infinity e raised to minus st e raised to minus st f of x dx. So e raised to minus st into f of x is a cos 80 dx. So here e raised to minus 80 give a Laplace transform e raised to minus 80 upon plus b square. So we apply in this example of the so we give a cos 80 plus b sin 80 into dx. So e raised to minus st upon minus a square plus b square. In this bracket a square put the limits are in this equation. So give a cos 80 plus b sin 80 dx. Limit e raised to minus infinity upon minus a square plus b square a cos infinity plus b sin infinity to dx minus lower limit e raised to minus 0t upon minus a square plus b square a minus cos 0t plus b sin 0 dx. So e raised to minus infinity are 0. So give an equation is 1 upon a square plus b square. So final answer is upon a square plus 1.
Everyone, my name is Ramesh Modi. Today I will explain the Laplace transform of t raised to n. So we will write for the formula. After that we will put the f of t is equal to t raised to n. After that we will put the st as u. So s of t is equal to u. So we will take s to as denominator is equal to u by s. So after that we will differentiate this term. So dt is equal to 1 by s into d. So after that we will put t is equal to 0, t is equal to 0, u is equal to 0, and t is equal to infinity, and t is equal to and u is equal to infinity. So after that we will put this value in this equation, in this formula. So what is the t value is u by s. After e raised to st we will write as u. We know that the dt value is 1 upon s into dv. So after that we will take the s raised to n plus 1 as a common. So we will get the next term as n into du. So after that we will take this 1 upon s plus 1 outside the integration. So this term will come u raised to n plus 1 and minus 1 du. So as we know the formula of the gamma function, so we will see what is the gamma function formula. Gamma function is equal to gamma of n 0 to infinity e raised to minus x and n raised to x minus 1. So we will apply this formula in this term. So we will get 1. So this term will come as n plus 1 gamma n upon s raised to n plus 1. We can write this transform as e raised to n factorial upon s raised to 1 plus 1 n plus 1. This is the formula of t raised to n. So